Given the nature of this semester and the fact that we're under a little bit of an emergency with the whole quarantining thing, I don't really have the time to treat Kirchhoff's laws in the rigor that I normally do. Consequently, what I want you to do is really read through this section in the book. I will talk through this and maybe set a couple of problems on this, but on the whole, we will not really be going into this in the depth I would like to. And Kirchhoff's rules are quite important, yet they do just boil down to a mathematical method every single time of solving simultaneous equations for a circuit. And Kirchhoff's rules are used to their best potential when we're looking at cases where there are multiple EMFs in a circuit and branches in that circuit. So taking a look at this particular diagram, here we have a battery with a voltage being supplied or a current coming this way. Here in this branch of the circuit, the current is coming this way. And the key to Kirchhoff's laws is choosing which direction currents are going and deciding which currents win and which way the current is flowing in your circuit. If you design a circuit badly, you may end up with a problem with dead spots, i.e. you could end up with one current going this way and another opposing it and end up with a dead spot, say no current flowing through this part of the circuit at all. So Kirchhoff's rules, or laws as they're written, are particular rules for solving more complex systems of resistors and batteries than we have seen currently. And here is a nice mess of cables. This is the kind of thing people do in India all the time when they steal electricity. I would not like to figure that out, especially with high voltage, dangerous electrical systems. There's a picture of Kirchhoff. Always like to throw the history in. This is the guy we're talking about. Another one of those people with a fantastic beard. 1824 to 1887, so he hasn't been around for a while. And here he is with Bunsen of burner fame. Not that Bunsen, not the Muppet. Get rid of that. But there's Kirchhoff with the particularly tall Bunsen. So this is the guy who is responsible for those burners you see in chemistry labs. And here's Kirchhoff, looking somewhat Abraham Lincolnish. And Kirchhoff came up with two laws. One a voltage law, two a current law. He also did a lot of things with optics and fluid dynamics and a lot to do with spectroscopy, but we won't get into that here. We're going to stick to his electrical work. So Kirchhoff said what was really a statement of conservation of energy. The sum of voltages around a circuit, a conducting loop, must be zero. So what he was saying was that all of the energy, all the potential difference in your loop is conserved. So since voltage and work are related, the net work done must be zero. So if you cast your mind back to mechanics, this was true for any conservative system. So Kirchhoff's voltage law, and you often see this truncated to KVL, was saying that as we go around this particular system, resistors will do work and a voltage will sort of default source here will supply work, will do work. So this will take work out of the system, this will put work in. Very much like forces and friction removing force from a system could be considered to be work being done by the frictional force and work being done by the force that you're putting in. The work being done to maintain the PD, to maintain the voltage, is done by the battery and work is taken out by the resistor. And neither can do anything else. If too much energy gets taken out, we won't actually violate conservation of energy. The resistor will burn out and explode. So it was all really based on conservation of charge. If you look at currents entering a junction, and by junction we mean a point where electricity can split in two ways, the sum of the currents entering a junction have to equal the sum of the currents leaving the junction. In other words, if current goes into a split, so it can go two ways, it will split into I1 and I2. So for a case of a series resistance, it's relatively simple. we'll end up with current traveling through here, and we'll have current supplied by two different batteries here. And that current, if we choose our loop around here, we could just sum up V equals IR for each of our cases here. Well, our current would just be whatever we're getting from both of these 1.5 volt batteries. So Kirchhoff's laws really are statements of conservation of energy. We have a current rule, and this states that the current is the same everywhere when there are no junctions. And we have a voltage rule, that all voltages increase and decrease and ultimately add up to zero. And to actually account for this, you have to make a trip around your circuit and count the voltage increases and decreases as you go around. And I would say definitely look at the examples that I have posted on this particular process, both animated and PDF. Now, in a lot of cases, you don't know which direction your currents are going, so you make a bit of a guess, and the more educated you become in this, i.e. the more examples you look at, the easier it is to guess whether things are going clockwise or counterclockwise. But you have to be consistent. You can't change the direction of your loops once you've started to go around. So, if we take our previous case and go clockwise starting at the lower left corner and add our voltage increases and decreases, we'll say 1.5 volts plus 1.5 volts minus 2 voltages lost to our resistors would come to 0. Then you can either figure out the currents or the voltages by V equals IR. You go through your system and replace all of your V's with I times R. So EMF, or the voltage from the battery, will be 3 volts, 1.5 plus 1.5, minus IR1 minus IR2, and come to 0. That's our statement of conservation of energy. So V is IR1 plus IR2. I, we said, would be the same for that whole circuit, so it factors out, giving us I times the equivalent resistance of the circuit, R1 plus R2, which is something we have seen before. And then you can string your resistances together for however many you have. So let's find the voltage loss or voltage drop across this system. What would be the voltage drop here across the 20 ohm resistor? We have a 9 volt EMF, a 60 ohm resistor, and a 100 ohm resistor. So using Ohm's law, V equals IR, 9 volts is equal to I times 180 ohms. So I must be equal to 0.05 amps. We're simply determining this unknown. So as the current is the same everywhere in the circuit, the voltage across the resistor, across resistor 3 specifically, will be I times R3. So V3 will be 0.05 times 20 ohms. That comes to a voltage of 1 volt. So that becomes 1 volt across the 20 ohm resistor. And of course, adding up all of these voltages should come to 9 volts. So here's a slightly more complex example. Here we have 3 resistors, one in each branch of the circuit. But when we take a look at this example, we have 2 potential difference sources, EMF1 and EMF2. And what this question is asking is to find the 3 currents, I1, I2, and I3 in the circuit. We know R1 is 100 ohms, R2 is 10 ohms, and R3 is 5 ohms. And we have voltages of 12 and 6 volts respectively. So how would we do something like this? Well, first of all, we'll apply our junction rule to point A. So one of the things to do when you're looking at Kirchhoff's laws is label the junctions. That way, when you're referring to them, you can say we have 2 loops, A, B, C, D on the top part, and A, E, F, B on the second part, depending which direction you go. So labeling your loops is fundamentally important when you're trying to convey what you're doing to another person. And we can say I1 here, this is I1 coming in here, is going to split two ways here. I2 through here, I3 through here. We don't need to apply the junction rule at point B because everything has been returned and everything's recombined and it's back to I1. So if we've got a look at our equation, it's automatically satisfied at this point. What we're going to do is apply our loop rule going around each of these loops in a clockwise direction. So we're going to go this way and look at all the voltage sources this way and all the voltage sources this way for this loop. Now, what we're going to do is if we're going with our current, we're going to end up with a negative. If we're going against it, we'll end up with a positive. So that means we'll have negative I2R2 plus V1 here, EMF1, minus I1R1 is equal to 0 for this top loop. We're taking into account I2R2 here, we're taking into account I1R1 here. There's our loop for A, B, C, D. So what we've done is take the terms involving the resistors and make them negative because they're going to be opposite to our current, to our EMF, I should say, the direction of current flow. So the term involving EMF becomes positive and EMF goes from the negative to the positive plate. Now let's do the same for the AEFB. In AEFB now, we'll have minus I3R3 minus V2 because you can see this is now in the opposite direction to this battery. So you have to look at the directions your batteries are hooked up. E2 or EMF2 is opposite in direction to EMF1 and that needs to be expressed here in our calculation. So minus I3 R3 minus V2 minus V1 plus I2 R2 because those negatives will flip will give us 0. And that's this loop. So we formulate our two equations, put them together, and now we can combine our junction rules. So we'll have R1 plus R2 factored out times I2 plus R1 I3 equals our first voltage source. The second loop can be rearranged now and put both of the EMFs on one side, giving us I2 R2 plus R3 I3. What we've done really is form a pair of simultaneous equations, one for I2 and one for I3. And what we're going to do then is just solve them like those simultaneous equations. To do that, you have to look back at the method of solving simultaneous equations a bit. And this just becomes a mathematical method from here on in with little physics. We multiply the first equation by R2, the second equation by R1 to try and get them in a similar form. And then we add the two together and that becomes this. R1 R2 plus R2 R3 plus R1 R3 times I3 will become negative R1 EMF1 minus R1 plus R2 times EMF2. Rearrange it for I3 and we'll end up with R1 EMF1 plus R1 plus R2 times EMF2 over all of this. R1 R2 plus R2 R3 plus R1 R3. So like I said, just mathematics here, no physics. We have all of these values. So I3 becomes negative 100 times 12 plus 110 times 6 over 1000 plus 50 plus 500 ohms, which gives us 1860 over 1550. That allows us to determine that I3 is now negative 1.2 amps. Now multiply the first equation by R3, the second by R1, take the difference of those two equations, and you get this. Rearrange it for I2 now, and we've got an expression for I2. Substitute in, and we'll get 1.2 amps. Now you've got two of the currents. So what we can say, if we have our values of I, we can say I1 was I2 plus I3. That becomes negative 1.2 plus 1.2, and we figure out that we have 0 amps flowing through here. So I3 is negative 1.2, and that indicates that current is 1.2 amps, but flowing in the opposite direction to I3. So that sign is important. It tells you the direction of your current in each case. The magnitude in this case is equal, the directions are opposite, and we'll end up with 0 amps flowing in this circuit. A very poorly designed circuit. Like I said, get an idea of how Kirchhoff's laws work. We don't have time to treat them as well as I would like to, and just understand how you formulate your simultaneous equations and then how you would solve for them. And formulating them and going around the loop and creating the right equations and the right expressions to start with is most of the battle. The rest is mathematics.